Hi, the section 8.3, 8.4, the testing contingency tables. So question, so are height and the academic performance of this table independent? You can see that if the students are lower, the shorter, it sounds the academic performance is better in this table. We have 80% good for the less than 150 centimeter, but the only 10 out of 10, 50% for students more than 150 centimeters. So we want to test if these two factors are significantly dependent or not. So null hypothesis is that these two factors are independent and alternative is dependent in some way. And the idea to test this table. So at first, calculate the subtotals. So we calculate this 20, 10, and the 18 and the 12. Then we calculate the expected number of observations when height and academic performance are independent. So you can see, for example, the more than 150 centimeters that we have in total 20 students, and actually the proportion of good and poor is the 18 to 12. That is the 60% to 40%. So then we have 12 observations. The expected value is 12 observations because the good is 60%. So if the height and the performance does not correlate each other, then the 60% of these 20 students are good. So this should be 12, and here is 8, just because 20 minus 12, or the 40% times 20. And in the same way, that we can get this 6 and 4. And the idea is to test this expected table. So difference between this expected table and actual table. If this difference is small, then we accept the independence. But if difference is very large, then we reject the null hypothesis that the two factors are independent. So difference or the distance, we want to measure the distance between these two tables. And if this is too large, then we reject the independence. So this kind of table is called the contingency table. So we have the two factors and eye color and hair color here, and then we have counts. So this is a famous the hair color, eye color data in the default R package. And this is the counts for the PhD program in statistics in old days in large university. So actually this has also the total and the subtotal here. And this is called contingency table, or sometimes the confusion matrix. And we say the number of rows here 3 as R, and the number of columns here we have 4. The total is not included, so 4. So this is R is equal to 4, 3, and the C is equal to 4. Okay, so now the formal procedure. So at first, in general, how to calculate expected table. So this explains how to calculate it. So at first, we count the marginal sample proportion. So if we have the 56 black hair students out of 233 total students, then we take the sample proportion, so 0.24, and we can do the same for all other marginal probabilities. So these are called marginal probabilities because this is just the margin of the table. Then next step, we assume the independence between hair color and eye color. If these are independent, then the probability of this, that is the black hair and the brown eyes, is the product of this probability and this probability. So if the event A and event B is independent, event of the A intersection B is the product of the A and the product of B. And in the same way that we can calculate these probabilities, so we can fill out the whole table. Then finally, we calculate the expected number of observations in each cell if two factors are independent. So we have already calculated the probability. So we multiply probability by total number of observations. Then we get the expected number. So then we can do the same for all cells. So we have the expected number here. Of course, the actual number should be an integer, but here this is just the expected number. So it can be fractional. So these expected numbers, we call it as the E sub ij. So for example, here is the third row and the second column. So E sub 3, 2. And also the actual number of observations, that is our observed table, that we say the number is O sub ij for ijth cell. Then finally, we want to measure the distance between observed table, OIJ, and the expected table, EIJ. So this is the distance. So we take the difference and take square, then take summation. So that is the usual way to define the distance. But if the EIJ and OIJ are larger number, then difference is naturally large. For example, you can see 1,000 and the 995. The difference is very small, negligible, but actually the absolute difference is 5. So this is the different from the smaller numbers. So for smaller numbers, even the 10% difference, we only have the difference of 1. So we have to normalize, standardize it in some way, and we divide this as E sub ij. So basically, this comes from the central limit theorem. So the variance is proportional to the reciprocal of the sample size. So we divide by basically expected sample size. Yeah, so then we can calculate the difference. So O11 minus E11, we have calculated the upper left cell, the expected value, and actual value is 32. So discrepancy is this difference between 32 and 22.8. Then take square, then divide by expected value. Then we add up all terms. So we have the 3x4 tables. So we have the sum of the 12 terms. Then we get 13.098. So if this is very large number, we reject the independence of two factors. If this is moderate number, we do not reject independence. So then what's the threshold? How large it should be to reject null hypothesis? So this comes from this theorem. So when all OIJs are large enough, say OIJ is larger than 5, then this chi-square statistic follows the chi-square distribution with df r minus 1 times c minus 1. So in the previous example, we have seen the r is 3 and c is 4. So that means that this is 6. So in the previous page, this statistic follows chi-square 6. So chi-square 6 has the expectation of 6. So 13 is somewhat large. And we can calculate the p-value based on this. So we take the chi-square distribution with the 6 degrees of freedom and take the 13.0 something. So 13.0 something, 0.10, maybe 0.9 something. So then we calculate here. So this is the p-value. So p-value is the probability that more extreme event than our sample happens under null hypothesis. So under null hypothesis, chi-square is smaller. So larger chi-square, we reject null hypothesis. Yeah, so this is overall explanation of the chi-square test on contingency table. So in the next video, we will explain with R code.